So, when you have a substance, it might be nice to know when the solid turns into a liquid, when the liquid turns into a gas. And as we talked about at the beginning, sometimes solids go straight to gases, and gas sometimes goes straight to liquid, or gases go straight to solid. So, this comes up with the idea then of what's called a phase transition. And a phase transition means you're going from one phase to the other. So, you're going from a solid to a liquid, or a gas to a solid. Any combination of those three is possible. When you have a phase transition, it's only possible through understanding kinetic energy and the intermolecular forces. And they're really important. They're around us all the time. If you've seen ice on your car windshield, that's deposition. If you've ever been for a run with a dog or another family member or whatever, that involves sweat, which vaporizes after a while. So these things are pretty important. Now, we're going to be using again the terms endothermic and exothermic. And endothermic means it needs energy to make it happen. Exothermic means energy is released when it happens. And both of those will be important. So the ones on the left are lowest kinetic energy. It also has the strongest intermolecular forces. And of course, that's solids. On the other hand, gases have the highest kinetic energy and almost no intermolecular forces. They're so independent of each other. So knowing how this all comes together, we can start figuring it out. So, within the same phase of a substance, you can figure out the energy required by using Q equals mc delta T. And C was the specific heat capacity for the substance. The amount is usually something measured in grams, and delta T will be the final minus the initial change for the substance. So Q equals mc delta T works really well if you keep it in the same phase. So, an example, if you were heating water from 25 Celsius to 90 degrees Celsius, you would use mc delta T. Your heat capacity would be 4.184. You'd multiply that by the amount. Your delta T would be final minus initial temperatures, and you'd be good to go. And Q, the sign of it, will tell you if it's exothermic or endothermic. So if you add energy, Q will be positive, endothermic. And if you get energy out, Q will be negative, exothermic. You can also, though, have a phase change, like you can turn a solid into a liquid, you can turn a liquid into a gas, stuff like that. And there's also a heat associated with that can be positive or negative, all right? Q, the value of Q, the amount of energy it's going to take or the amount of energy you're going to get out, depends on the amount times the delta H of a phase change. Now, delta H is enthalpy, and there's lots of different delta H values. So, for example, there's a delta H of vaporization, which gets delta H vap. And if you want to turn that poor chocolate bunny up there into a liquid mess, you're going to have to turn the solid into a liquid. I would believe that's what it's turning into there. There's going to be the amount of the rabbit times some type of delta H for the process, and you can actually figure out Q. Q values, again, will be joules or kilojoules, and as long as you have the right values, you can figure out anything like that you want to. Sometimes you'll see pictures like this, and enthalpy, H, is on the left-hand side. So that's the Y energy axis. And they can be kind of confusing, but here's the general idea. Anytime you go from a solid to a liquid to a gas, or if you go directly from a solid to a gas, endothermic. It's going to be a positive energy value. You're going to need to put energy in. So if you look at the up hand left arrows there on the left side, the biggest one, sublimation, that's the energy to go from a solid at the bottom to a gas at the top. It's going to be endothermic, and it's usually a very big number. On the other hand, if you go from a solid to a liquid, that's the melting process. That's an energy, but it will be positive. It'll take energy. Liquids to gas you have to vaporize the gas, so that's vaporization. So these are the terms that we'll use: sublimation, solid to gas; melting, solid to liquid; vaporization, liquid to solid, etc., etc. On the other hand, if you're going from a gas to a liquid, from a liquid to a solid, or from a gas to a solid, those actually give energy off. Those will be negative numbers. So if you look on the right-hand side, the blue arrows, Condensation is the energy, the delta H value, that goes from a gas to a liquid. Freezing is a delta H value that goes from a liquid to a solid. And deposition is the fancy name for when a gas goes directly to a solid. But the important part for us here is those are all exothermic. The ones on the left are endothermic. You have to put energy in. The other side are exothermic. Now, why this is happening? On the left-hand side, solid to gas, solid to liquid, liquid to gas, you're breaking intermolecular forces. And that's not going to happen just by looking at it. You have to add energy. So all of those are positive to break. You're adding more kinetic energy to break the intermolecular forces. On the right-hand side, if you go from gas to solid, gas to liquid, liquid to solid, then you're going to get energy out because the kinetic energy that those systems had is being gotten rid of and the intermolecular forces start taking over. Those all release energy. So this is important. Solids to liquids, liquids to gas, always endothermic, always going to be positive Qs. Gases to liquid, liquid to solid, always exothermic. Those will always be negative Qs. The Clausius-Clapeyron equation is an equation that's used often to figure out things like the heat of vaporization. It can be used for lots of these different delta H values we're going to talk about, but the delta H vaporization is real common. And so these scientists figured out, which is a testament to their power, if you make a plot of the natural log of pressure, vapor pressure, versus 1 over the Kelvin temperature, you actually end up with a straight line. And if you remember from the graphing lab, this is a kind of problem you can apply a linear regression to. And a linear regression will give you the slope, the y-intercept, and the correlation coefficient. Well, the slope here is the important part. Slope equals minus delta H vaporization over R. And R is the so-called energy R constant, 8.3145 joules per mole Kelvin. So this is a great way to find delta H of vaporization if you have lots of values. Now, if you only have 2 values, you can use this equation right here. It's not as good of a method as plotting natural log of vapor pressure versus 1 over temperature for lots of different points. But if you only have 2 values, this will work. You can get a delta H vaporization out that way. So this is how these numbers come around. We probably won't do a lot with this because it's kind of crazy, but it is something you can do. All right, you'll take the natural log of vapor pressure, plot 1 over the Kelvin temperature, and be good to go. Now, we can use those heats of vaporization and other delta H terms, as well as Q equals mc delta T, in problems like this. So let's say that the scientist wants to know the quantity of heat in kilojoules that's required to melt 500 grams of ice, which is at 0 degrees Celsius, and heat the liquid water, to steam at 100 degrees Celsius. So we're turning ice at 0 to steam at 100, all right? And to solve this problem, we need to basically have 3 steps. And I'm going to show you on the graph here. First of all, we're starting at ice at 0 degrees Celsius. And the first part we're going to do, I'll call it number 1, we're going to melt the ice. We're going to turn that ice into a liquid. That's going to be the mass of the object times one of those delta H things. And that's going to allow us to calculate Q, the energy required. And then the second part is on this kind of diagonal line right here. That's going to be the energy required to take the liquid water at 0 Celsius and turn it to liquid water at 100 Celsius. So number 2 is going to be Q equals mc delta T. We'll use the mass of water times 4.184, the specific heat capacity, times the delta T, which will be 100 minus 0, to figure out what that value is going to be. And then finally, step 3, we're going to take that liquid water at 100 degrees and we're going to turn it into steam at 100 degrees. So we're going to use the mass of the object times some type of delta H vaporization, which is the energy required to vaporize it, to figure out the Q part there. So we're going to have 3 calculations, step 1, 2, and 3. They're all going to be positive numbers because we're turning a solid into a gas. That's always a an endothermic, always positive numbers. And it's not too bad. Just make sure that you break this down into separate sections and then add those results all at the very end. A couple of things. Temperature is a constant while the ice melts. So temperature, you can see, is on the y-axis right there. And you can see, I'll highlight it in blue, that part is totally flat. So you're not changing the temperature as you melt the ice, all right? That's why that part, when you have a phase change, it's the mass of something times the delta H of that quantity, all right? But there's no temperature component in that part right there. When you heat the water, this part right here, you do have a temperature change. You're going from 0 Celsius to 100 Celsius. Your delta T, which can be in Celsius or Kelvin, I would definitely use Celsius here, will be 100. We'll use the specific heat capacity for liquid water, 4.184, which I really want you to know / memorize, and we'll multiply it by the mass to get then that value. And then the final part here, where we're evaporating the water, which I kind of circled over part of it, sorry about that. You can see again, there's no temperature change, all right? We are literally turning the liquid molecules into gas molecules. We're breaking the intermolecular forces in the liquid and turning it into gas, which has no intermolecular forces. So it's a whole different environment. Now, the length of those lines will be proportional to the energy. And you can see that the green line is a lot longer than the purple or the blue lines. So that's probably going to be the biggest of our calculation numbers here, as we'll see. But at the very end of this problem, we'll add the amounts from the blue, the purple, and the green together to get the overall energy. No problem. We will need some constants to figure out this problem. Now, the specific heat of liquid water, again, is something I'd like you to know, 4.184 joules per gram Kelvin. But here are two other numbers we'll need, and I would always give you these numbers, by the way. The delta H of fusion, the enthalpy of fusion, sometimes called heat of fusion, for ice is 333 joules per gram. So what that says is that 1 gram of ice is going to require 333 joules to turn solid into liquid. The heat of vaporization, delta H vap, is 2260 joules per gram. So every gram of liquid water needs 2260 joules to turn it into a gas. So notice it's quite a bit more energy to turn liquids into gas than it is solids into liquids. Just kind of an interesting phenomenon. To do this problem, we have the mass, 500 grams of ice, and that mass is going to stay constant as we turn it into a liquid and a gas. It's not going to change. We're starting with ice at 0 Celsius, and we're turning it to steam at 100. So the first thing we're going to do is we're going to figure out the energy required to melt the ice. We'll use the heat of fusion. So the amount times the delta H of fusion will be 500 grams times 333 joules per gram, 1.67 times 10 to the 5th joules are required to melt the ice at 0 Celsius. Step 2, we're going to raise the water from 0 Celsius to 100 Celsius. This will be Q equals mc delta T. So the C value is 4.184. The mass is still 500 grams. Delta T can be Celsius or Kelvin. It doesn't matter. It's going to be delta T of 100 either way. 2.09 times 10 to the 5th joules. And then the final step will be to evaporate the water. We'll have the amount, again, times the delta H of vaporization in this case, 500 grams times that 2260 joules per gram value, 1.13 times 10 to the 6th joules. So the final step, we're going to add the 1.67 times 10 to the 5th number to the 2.09 times 10 to the 5th number, and add that to the 1.13 times 10 to the 6th number. Add those up, you get 1.51 times 10 to the 6th joules. If you divide that by 1,000, you get kilojoules, 1,510 kilojoules. And that is the energy required to melt 500 grams of ice and turn it into steam at 100 degrees Celsius. Notice it's a positive number. It's endothermic. This isn't going to happen by itself. You must add energy to make this happen. Another kind of fun thing, if you wanted to turn the 100 grams of steam at 100 degrees Celsius to ice at 0 degrees Celsius, and it was the same 500 gram amount, the overall energy would be the opposite sign of what we just calculated. So turning the gas into a solid again, you would get out negative 1,510 kilojoules. It's the same process, just reversed. You can do that with these Q and delta H signs. Kind of cool. A phase diagram shows all different phases of a particular substance, and it shows rough values, at least, how to go from one point to the other. So most of these phase diagrams look kind of like a Y. So if you use your imagination, there's like a Y right there. The solid-liquid interface is the first part of the Y. The liquid to gas part is the second part of the top part of the Y. And then the solid gas at the bottom is like the base of the Y. If that works for you, cool. If it doesn't, don't worry about it. I'll try and show it. But anyway, in a phase diagram, you almost always have pressure on the Y-axis and temperature on the X-axis. And then the solid is almost always in the far left side. The gas is basically the far right. And the liquid is the middle part of this so-called Y. And so it'll show you where solids go to liquids at a certain pressure, where liquids go to gases. And also it can show you, for example, where solids go to gases there at the bottom. But along the way, there's some interesting things we'll talk about here. A triple point is fascinating. It's where you have all three phases at the same time. So imagine if you had an ice cube in liquid water with gaseous steam over it. That would be the triple point, for example, for water. So we'll talk about these. Phase diagrams are super helpful to geologists, to engineers, to anybody working with many phases of the same material at the same time. And we'll kind of see how this works out as we go through. This is a phase diagram for water, all right? And water, of course, is so important to us in so many ways. Now, water is a lot of points that we know at 1 atmosphere of pressure, which is 760 millimeters of mercury. So let's kind of visualize what's happening in each one of those sections. So imagine that we have solid water, an ice cube, all right? And we could view into it. So that little animation there shows what the ice cubes are doing. They are moving around. It's not a lot, okay, but they are moving. Even that movement would stop at 0 Kelvin. That's where absolute zero becomes a handy reference point, because at 0 Kelvin, even those kind of movements would stop. But solids do have some movement to them. You can see that's what's going on. Now, as you raise the energy, you get to the point where the solid starts to turn into a liquid. And this would be an animation kind of showing it. So you got the solid on one side and the liquid there to the right on the other. This would be the melting point if it was a solid, or freezing if it's liquid going to solid. And you can see that both phases are around at this point. This question shows a phase diagram for oxygen. And oxygen has a solid, liquid, and gas or vapor phase, just like the water one did. And you can see the different points. Now, there's 1 atmosphere on the top, 760 millimeters of mercury. But notice that the temperature down there on the bottom is not even close to room temperature. Room temperature is like 298 Kelvin. And this phase diagram there has a highest point of roughly 90 Kelvin. But that's not why I'm asking this question. Here's the interesting thing. I want you to focus on the solid-liquid slope. I want you to focus on this part right here, which is the interface between the solid-liquid phase. Now, if a slope is positive, and this comes from the graphing lab, if a slope is positive, it increases up and to the right. And if you have a negative slope, that would be something that increases up and to the left. Now, the solid liquid line for this oxygen right here, you can see it's increasing up and to the right. That would be a positive slope. And what that actually tells chemists something which is amazing. If you have a positive slope, your solid phase will be more dense than the liquid phase. So looking at the phase diagram for oxygen, all right, we have a solid slope. And what that means is that if you had a solid piece of oxygen oxygen and you placed it in liquid oxygen, the solid oxygen would sink to the bottom. The liquid would be over the solid. And again, why that's kind of cool is that when you see water here in a little bit, water has a negative slope. Negative slopes mean that the liquid phase is more dense than the solid phase. So the ice cube floating on liquid water, again, very, very rare, but you can quickly tell from a phase diagram if that's true or not by the slope of the line. So positive slopes are what you're going to see for these phase diagrams most of the time. Solid phase will be more dense than the liquid, solid will sink. But for water and just a couple other substances, you do have a negative slope. That means that the solid phase is less dense than the ice will float on the liquid water. It's kind of a cool thing. It's very rare. That's why I'm kind of highlighting it here. But anyway, hopefully you can share some of my excitement with me. Here's an animation of the liquid phase, and liquid molecules do have some intermolecular forces, not as tight as the solid, but it's keeping it together. But more importantly than not, try to focus here on the slope of the solid liquid line. And you can see that that line is increasing up and to the left. Oxygen was up and to the right, but water is up and to the left. So that means that the liquid phase is more dense than the solid phase. Solid ice cubes float on more dense liquid water. It's kind of a cool thing, and again, it only happens for water and a couple other groups. Now, when you increase the temperature even more, you get to the point where you're in equilibrium between the liquid and the gas phases. So then you have liquid and gas at the same time. So as you vaporize a liquid, the liquid turns into a gas. On the other hand, if you condense the gas back to the liquid, that would be condensation. So both of those would involve that interface right there where you have both phases running around. Eventually, you'll get to just the gas phase. Gas molecules have no intermolecular forces, at least for us, interacting between them. So a lot of kinetic energy, like there's a lot of movement around. The solids had hardly any movement. They have very low kinetic energy. Gases have a lot of kinetic energy. So even though the little intermolecular forces are trying to form, that high intermolecular forces rips them apart before anything noticeable happens. That's why we say that gases have no intermolecular forces. Solids will turn into gases directly, and every substance has a certain pressure and temperature where this is possible. So you can see where that line is kind of focusing on. For water, that's at a pressure less than 4.58 millimeters of mercury. It's a very, very, very low pressure. The temperature is about 0 Celsius. That's not so wild, but you do need a super low pressure. And that's why we're not used to seeing solid ice turning into a gas or gaseous water turning into solid water. Most of the time, we're at 1 atmosphere pressure, which is at the top part of that graph. Solid goes to liquid, liquid goes to gas, and we're good to go. However, all substances also have what's called a triple point, and triple points have all 3 phases present at the same time. And water has one, and acetone and ethanol and every substance you know should have a triple point. Triple points are very specific for pressure and temperature. And so for water, if you're at almost 0 Celsius, 0.01 Celsius, and your pressure is 4.58 millimeters of mercury, and remember normal pressure is about 760 millimeters of mercury, then you can get all 3 phases at the same time. So you'd see like an ice cube, liquid water, and gaseous water all happening at the same time, which is pretty crazy. Here's the phase diagram for oxygen once again, and it says what is the point called where you're at pressure of 2 millimeters of mercury and a temperature of 54.34 Kelvin. So to read this table, the pressures are on the y-axis. That number right there is the 2 millimeters of mercury. And here's the 54.34 Kelvin temperature. And if you go up, notice you're right at the intersection of the solid liquid gas line. So that's called the triple point. All right. Triple points are where you have all 3 phases at the same time. So that would be the triple point. This picture shows water at the triple point. And again, it's kind of hard to show in a picture, but you can see that you've got solid like ice forming. You've got the liquid water under it, and there is water vapor over it as well. So water is really important, and you should know these, and I hope you know them already, but the normal boiling point for water is 100 Celsius, and the normal freezing point is 0 Celsius. And that happens at 1 atmosphere, which is 760 millimeters of mercury. The triple point is just something we're not used to. It's about 0 Celsius, but the pressure is so low. And normally we don't have pressures like that we deal with in our day-to-day lives.
It's the whole thing just gone. Oh,
It's gone crystal.
I was about to say I think the whole thing's solid, and now it's. Jesus.
This is kind of cool. This compound is called cyclohexane. It's an organic chemical. But anyway, this is at cyclohexane's triple point, 6.33 degrees Celsius and 40 torr, 40 millimeters of mercury. So this is something that's easier to do in the lab than, say, water. But you can see there that there's liquid at first. The liquid turns into a solid, the ice kind of forming. And then all the bubbles, that's the gas phase. So all three phases are present at that point. Pretty wild stuff. The critical point is another point that is sometimes shown on these phase diagrams. And at the critical point, all the substances turn into what's called a supercritical fluid, SCF. And these supercritical fluids are just wild. It only happens usually at very high pressures and temperatures, but there are some kind of cool things. And the classic example of a critical point is for carbon dioxide. Now, carbon dioxide is nonpolar. And when supercritical fluid of carbon dioxide is used on coffee beans, it's able to extract the caffeine from the coffee. So all the decaffeinated drinks you have are basically the result of using these supercritical fluids, specifically CO2 on the coffee bean. So the decaffeinated coffee bean is left, and the caffeine, which is extracted from the CO2 then, can be used, and that's what's used to make sodas and energy drinks and stuff like that. So pretty crazy. So for water there, the supercritical point this critical point is 374 Celsius and 218 atmospheres. So that's a lot higher than we could probably honestly get to at Mount Hood. But if you're in an industrial place or a higher institution, you could totally get those kind of pressures happen. So anyway, the densities of the liquid and gas phases become equal. You basically have this supercritical fluid running around, and it's pretty interesting. But again, all the caffeine that comes in everything caffeinated except for coffee, you have to get through these kind of processes. In this next section, we're going to look very briefly at the solid state of matter. So most of the time so far, we've talked about liquids and how to go from gases to liquids to solids and vice versa. But solids are also really interesting. Now, solids, this is a huge topic, and we're not going to be able to do justice to it. But let's kind of have some overview and kind of get some examples of what you could see if you look more at this in the future. So when it comes to all of the solids that science knows about, there's two forms. One is called crystalline, and in a crystalline solid, all the particles are in a highly ordered arrangement, and they're repeatable. So the part at the left would be the same as the right, which is the same as the top and the bottom, stuff like that. There's also a huge type of solid category called amorphous solids, and amorphous solids don't have a particular order and arrangement of particles. And these will be things like clay and dirt and stuff like that. We're only going to focus on crystalline solids in this section because we're kind of limiting here what we can do. Crystalline solids have repeatable patterns, so it makes them a little bit easier to talk about, honestly. But amorphous solids are very cool, lots of neat uses for it. It's more than we're going to get into in this part of Chemistry 222. If you have a crystalline structure, the molecules, atoms, ions, whatever you're talking about, are locked into what's called a crystal lattice. And crystal lattice are these small repeating units that go over and over and over within the solid. And they're very, very strong. That makes solids basically incompressible. So liquids you can't compress very well. Gases you can compress really well. But solids are almost impossible to do anything with. They're going to be there. Very rigid. You'll have cleavage lines where they break off, but you won't be able to change them. Pretty cool. Unit cells in all of the world's known solids can be broken down into 7 types. They call them the Brevis lattices, or unit cell types. And the names of them are there: cubic, tetragonal, orthorhombic, etc., etc. In this class, we're only going to look at cubic unit cells. And the different properties of all of them are listed there on the left. But if you look at the top one, that's the cubic unit cell. And we're focusing on cubic cells because of 2 things. First of all, the lengths of all sides of these cells are the same. So A and B and C are all the same length. It's a cube. Also, the angles that are within that particular molecule are all 90 degrees. And that honestly makes the math a lot easier. So we're only looking at cubic unit cells. We're only looking at crystalline solids. So you can see we're really limiting ourselves here to what we're looking at. But again, this is just a crazy section, and we're going to keep it somewhat simple. So we're going to talk in this section about simple cubic, face-centered cubic, and body-centered cubic systems quite a bit, all right? But I want you to know that outside of our little Chem 222 world, there's lots and lots and lots of different variations here, and we're just barely touching them. But this will give you an idea of how this works, and if you have to work on the other systems in the future, you absolutely can. So there are 3 types of cubic unit cells, and all the 3 types I'm going to show you here, they all have similar lengths. So length, width, and height, they're all the same value, whatever it is. Also, the angles are all 90 degrees, and that makes the math a little simpler. You don't have to use sines, cosines, stuff like that. And the 3 types are called simple cubic, which we'll abbreviate SC. A simple cubic cell just has an atom in each corner of the cell. So there are 8 corners in a cube. Each of them has an atom there. That's called the simple cubic, and it is the simplest one, as we'll see. The next one we'll talk about is called a body-centered cubic, or BCC. Now, body-centered cubic is the same as the simple cubic. There's an atom in each corner. However, body-centered cubic has, if you look carefully, 1 atom in the middle of the cube, in the body of the cube. So body-centered cubic is like simple cubic with 1 atom in the middle, and that'll be important to us here in a little bit. The last kind is called face-centered cubic, FCC. FCC is like SC, simple cubic. There's 1 atom in each corner. But if you look carefully, every face of the cell has an atom in it. Now, a cube has 6 faces: top, bottom, left, right, forward, backward. Each of those faces has an atom in it. Does not have an atom in the middle like the body-centered, but there is one in each face. So simple cubic, body-centered cubic, face-centered cubic are the 3 types of unit cells, and we'll see how they can be used to describe the properties of metals and stuff like that.
A simple cubic unit cell has 1 atom at each corner of a cube. The cells stack together to form a solid crystal, the overall shape of which has square edges. Each ion is shared by 8 different but connected cube cells. The arrangements of body-centered cubic and face-centered cubic unit cells are similar but more complex.
We'll talk about these unit cells a lot here in a little bit, but just remember in the back of your head that all of these are just the smallest repeating unit of what you would see in a sample of the substance you're talking about. So if we talk about, for example, the copper cubic unit cell, we'll talk about one of these little unit cells, and that will repeat over and over and over again in a sample of copper. Remember, in any sample, you're going to have 10 to the 23rd or so Avogadro's number worth of atoms, but on the smallest level, they all repeat. They'll all be in these same patterns. So on the upper right-hand side there, you can see, especially on the right, that little tiny atom that's there in the middle is actually connected to 8 different cells, all right? There's 8 little cubes that it belongs to. It's not part of just one cube, but it's actually part of many, many different cubes. And so in the unit cells, like in the lower part there, the kind of green part there would represent one cube. But each of those central atoms, those corner atoms, is actually part of other cubes as well. So we'll see how this all fits together. It's pretty neat how Mother Nature makes these repeating units, and we can use this then to understand the properties and stuff like that. The simple cubic unit cell is literally just where you have an atom in each corner of the unit cell. But you can see on the left-hand side there's 2 representations. The top part shows the actual atoms, which are basically spheres. The bottom part, though, is important. It shows what the unit cell would look like if you take, if you will, like a chainsaw and cut off all the parts of those atoms that aren't in the unit cell. And what you see right now in that video, that shows the chainsawed parts that are left, all right? And you can see that those atoms, even though it's a whole atom, only 1/8 of the atom is still in the unit cell. And the other 7/8 of the atom belong to different unit cells that repeat over and over and over again. So one thing that chemists talk about is how many net atoms are in each of these unit cells. And each of the simple cubic unit cells represents 8 atoms, but only 1/8 of them are inside. So 8 times 1/8, each simple cubic unit cell is 1 net atom. You have 8 times 1/8 atoms, which is 1 net atom, which is pretty cool. That's why sometimes people like these chainsawed versions, if you will. It shows only the 1/8, which is inside the cell. And since each corner represents an eighth and there's 8 of them, that's 1 net atom. The other thing we'll talk about when it comes to simple cubic unit cells is the ratio between the edge and the radius. And for the simple cubic unit cell, the edge of a cell equals 2 times the radius. And you can kind of see this one visually because when you cut off the parts that aren't there, like you have like 1 radius there on the top and 1 on the bottom, and they touch, so the edge, which is length, width, or height, either one because they're all the same, the edge equals 2 times the radius. In the lab, the solids lab, there's some more descriptions as to how this all works out if you're curious. If geometry is your thing, this will be a section for you. It'll talk about how the edge is equal to 2 times the radius, etc., etc. But punchline, at the end of the day, when you hear simple cubic unit cell, think 2 things. Think 1 net atom per simple cubic cell, and also think edge equals 2 times the radius of the atom. Those 2 things will help you go forward. The body-centered cubic is similar to simple cubic. There's 1 atom in each corner, but there's also an atom in the actual central part of the cell. So if you use the chainsaw on it, you have the 8 times 1/8 corners like before, but you still have that 1 atom in the middle. So when scientists talk about the number of atoms in a body-centered cubic, it's not only 8 times 1/8 of the simple cubic, but you also have 1 in the central. So there's 2 net atoms per unit cell. I'm not going to go into the geometry of how the edge to radius ratio was figured out, but when you do the geometry, the edge of a body-centered cubic unit cell equals 4 times the radius divided by the square root of 3. And you can check out the lab for more information on that. Body-centered is a little bit more common than simple cubic because you end up with 2 net atoms per cell instead of 1. It's a more efficient type of packing, and the more efficient it is, the more atoms you get in, it's better. We'll talk more about this in the solids lab. The face-centered cubic unit cell is also known sometimes as the cubic close packing cell, and there are subtle differences between FCC and cubic close packing, but we're not going to worry about them in our class. When you take the chainsaw to the face-centered cubic, you still have the 8 times 1/8 atoms in the corner. But the difference now is the face atoms, half of the atom is in the unit cell and half of the atom is outside the cell. So when you want to know the number of atoms in a face-centered, you have 8 times 1/8 for the corner atoms as before, but now you have 6 faces, and each face has half of an atom left once you take the chainsaw to it. So 6 times 1/2 are the number of atoms in each face. 6 times 1/2 is 3. And you add that to the 8 times 1/8 atoms in the corner, which is 1. 3 plus 1, 4 net atoms per FCC unit cell. And the edge to radius ratio for FCC is edge equals 4R divided by the square root of 2. And you can look in the solids lab for more information on that if you're curious. But again, punchline, when you hear FCC, think 4 atoms per cell, and edge equals 4R divided by the square root of 2. Here's a problem you might see. It says the unit cell for a metal is found to have 2 atoms per unit cell. What kind of unit cell does this represent? And there's all those different choices right there. Well, if you remember from what we just talked about, simple cubic, answer A, is 1 atom per cell. Answer C, face-centered cubic, is 4 atoms per cell, and face-centered cubic is the same, for us anyway, as cubic close packing, the CCC, answer D. But body-centered cubic, BCC, that has 2 atoms per cell. So the answer here would be B. BCC, body-centered cubic, 2 atoms per cell. Simple cubic, 1 atom. Face-centered cubic, 4 atoms. CCP is for us the same as FCC. There's actually differences, but we're not going to go into it. Good to go. The metals on the periodic table often fall in one of these categories. So simple cubic is very rare. It's only in polonium, which is quite dangerous and stuff, but it is actually simple cubic. Body-centered cubic, almost all the alkali metals and some of the alkaline earths and a couple of the transition metals use body-centered cubic for packing. But by far the biggest one is face-centered cubic. Now, face-centered and hexagonal close packing, which is also close packing, the CCP version, is what most of the metals are. But again, most of the metals fall in one of these categories. So by studying these types of unit cells, you can represent the bonding and the patterns for the different metals. Most of the metals on the transition metals, not all of them, all right, like manganese and lanthanum there, and mercury for that matter, have their own things going on, but a lot of them fall in one of these, which is kind of cool. They use X-ray crystallography to tell the unit cell types. And X-ray crystallography is a fantastic phenomenon. An X-ray is created. It's sent through what's called a double slit to create basically like a line of X-rays. And when they send the line through a crystal of these solids, a pattern emerges on like a piece of photography paper, like a picture. And they can interpret that back into the unit cells of face-centered cubic, body-centered cubic, and simple cubic. It's a fascinating process. It's definitely more than we need in Chem 222, but it is how they use it, and it's a very well-established pattern. If you're an X-ray crystallography person, you will have the opportunity to join many research groups. You'll do the X-ray work for them, and you'll be added into research papers. It's pretty cool. So let's look at an example of how you can find out if a metal is simple cubic, body-centered cubic, or face-centered cubic. And we'll use this example with aluminum. And aluminum has a density of 2.699 grams per centimeter cubed. The radius is 143 picometers, and we can actually use this information to verify that aluminum is face-centered cubic. All right. Now, at first, this might seem like a daunting problem, but it basically comes down to unit analysis, and we'll talk about some strategies to solve these in the solid lab. But if you look back at the face-centered cubic system, there are 2 important aspects of FCC, and the one we're going to start with here is edge equals 4 times the radius divided by the square root of 2. All right. It also, FCC means 4 atoms per cell, and basically what we're going to do is we're going to use the edge to radius ratio and then solve for how many atoms are inside the unit cell. Start with 4 times the radius divided by square root of 2. The radius is 143 picometers, which is very small. 4 times 143 divided by the square root of 2, 404 picometers. Now, in the next step, we're going to take the edge and we're going to cube it, because edge is length, and length times length times length equals volume. But because these are cubes, length, width, and height are all the same. So edge, which is is length. Edge cubed equals volume. We're going to turn this edge into a volume. But if we do an edge in picometers and we cube it, we're going to get a volume of picometers cubed, which is quite crazy to deal with. And if you look at these values, density is in centimeters cubed. So what we're going to do first, before we cube it, is we're going to take that edge and turn it into centimeters. Now, a pico is 10 to the minus 12. So a picometer is 10 to the minus 12 meters. That would allow you to go from picometers to meters. And then a meter centa, is 10 to the minus 2. So a centimeter, 10 to the minus 2 meters. I'm skipping the meters in this conversion. I'm going directly from picometers to centimeters. And when you do that, it's 10 to the minus 10 centimeters per picometer. And I recommend that you kind of work through that so you know how this all goes. But at the end of the day, 404 picometers is 4.04 times 10 to the minus 8 centimeters. Now that we have an edge in centimeters, edge cubed equals volume. As long as the length, width, and height are all the same, you can just cube the edge to find the volume. So 4.04 times 10 to the minus 8 centimeters cubed in your calculator is 6.62 times 10 to the minus 23rd centimeters cubed. Cubed is usually on your calculator. There's different ways to do it. You might have a y to the x button, which will allow you to do it. Also, if you have what's called the caret, which looks like an arrow pointing up, you can go caret cubed to do that. Figure out how to do this process. It will be handy in this particular section. And if you cube 4.04 times 10 to the minus 8, you'll get 6.62 times 10 to the minus 23rd. It's a nice way to kind of check yourself. This volume is very small, but even though it's small, we can use the density, which is given, to find the mass. So we're going to take the volume we just calculated and multiply it by the density. The centimeters cubed cancel. 1.79 times 10 to the minus 22 grams per unit cell. And again, that's pretty small, but these unit cells are pretty small, so it's kind of interesting. The molar mass of aluminum is 26.98 grams per mole, and Avogadro's number is 1 mole per 6.022 times 10 to the 23rd atoms. And if you take these numbers, you can see that the mole is a common denominator. So what we're calculating for right now is the number of grams in an atom, the mass of grams in an atom. So 26.98 divided by Avogadro's, you get 4.480 times 10 to the minus 23rd grams. And that's the grams per atom. And again, pretty small, but this is actually something you can do with math. Woohoo, math is fun. Anyway, that's the mass per atom. So earlier we saw that there was 1.79 times 10 to the minus 22 grams in a unit cell. And what we just calculated here is that one atom of aluminum, 4.480 times 10 to the minus 23rd. And when you multiply these together, you can see that you end up with atoms per cell. The grams cancel out. It comes out to be 3.99, which is awfully close to 4 atoms per unit cell. FCC. So we have just verified here that aluminum is a face-centered cubic. If we would have come up with a different number of atoms per cell, it would have been not face-centered cubic. But 4 atoms per cell means it's FCC. Pretty cool. So this gives you a kind of an idea how these problems work. The one thing I want to highlight is that you'll usually have a radius in picometers, sometimes angstroms, whatever. You want to convert those to centimeters before you cube them, because it's much easier dealing with centimeters cubed than it would be picometers cubed or angstroms cubed. And again, we'll talk more about this in the lab. There are many other types of crystalline solids, though, besides the metallic ones that we just talked about. There are ionic solids, covalent network, molecular, all different kinds of things. So diamond, as an example, is a covalent network kind of system. It's really crazy. So we're only looking here at crystalline solids, and it ignores all the amorphous ones. And we're only looking at the cubic unit cell ones, too. We're ignoring all the other types. So again, this is a very primitive introduction to solids, but you kind of see what's happening. Almost all of them break down to some, at least the solid crystalline ones, break down to some kind of small repeating unit, and from there you can make predictions on it. It's pretty cool kind of stuff. So that's the end of chapter 10, and I sure appreciate you all being here. There are more resources to help you really knock this material out, study guide, concept guides. I do have some handouts which might be helpful. There's a guide to the intermolecular forces to help you learn those. There's also a cubic unit cells guide. It talks about how to go from one to the other, and it does list the number of atoms per cell as well as those important edge to radius ratios. You can absolutely reach out to me if you have questions on anything. You can talk to the Learning Success Center / Avid Center located above the library on Mount Hood Community College's campus. Lots of ways to get assistance. Thanks for spending your time with me. I hope this has been a helpful use of your time. And again, if you have questions, let me know. Have a great day.